Thermodynamics, yes, ma'am.
Yeah, and just give me a sec. I'm just opening it up. I was caught in high fever, so I was even not able to take the class. Even it's going so much in trouble
It's
now.
fine, ma'am. It's
Yeah.
fine, ma'am.
Okay. So I'm starting with your B4 topic, and that is thermodynamics. Okay. Now check. In this particular topic, we are having, yeah. So coming back to the topic, what do we understand by thermodynamics? Yes. Do let me know. Are you aware what is thermodynamics?
Yes, ma'am. I have studied it. I'm trying to recall thermodynamics. Yes.
Yeah, say, I'm listening. It's okay.
Like, for example, if we have like we have like a system, ma'am, and we have a like heat transferring from one place to another, something like that. From one
Okay. So let me
from one
explain this
system to another
terminology to
system.
you. Yeah. Let me explain this particular terminology to you. What happens over here is, Akshita, we basically explain the transfer of the heat. Okay. And that has been explained, I should say, between the system and the surrounding. In the last class, I had explained you this terminology, that what is system and what is surrounding, right? So in system, between system and the surrounding, we actually study the exchange of heat part. So that is known as thermodynamic study. Okay. So the part of the physics is doing the study of this thing. Okay. Where we actually try to understand that what type of, I should say, heat exchanges are taking place between the system and the surrounding. Now the part of system and the surrounding is connected in such a way that if suppose this is system and this is surrounding, okay Akshita, then with the surrounding what is connected, that around any particular event, okay, whatever we are observing is nothing but its surrounding, and the event itself which is happening is nothing but the surrounding. Understood?
Yes, ma'am.
Like example, bonfire. If I take the example of bonfire, here are the sticks which has been placed, and here is the particular fire which is coming up. So this is my system, and how it is changing the heat part with the surrounding, that is when we are doing study, it will be calculated as your thermodynamics. Understood?
Yes, ma'am.
Okay. Now, there are some other studies also, like if I take this other, I should say the definitions for all these terminologies, then I will define my system as, wait, I will define the system as it is the body that we are considering. Okay. What is surrounding now?
The place where the energy transfer is happening.
Yeah. So surrounding is basically uh, that system, I should say, which is interacting. It should not be mentioned as
Hello.
yeah, just wait. Basically, this page had become irresponsive. I'm sharing another page.
Yes, ma'am.
Check. Is it visible
Yes. Ma'am.
clearly?
Yes, ma'am.
Great. So basically, what I was telling is system and surrounding done, and then the system and the surrounding constitute the universe. Understood?
Yes, ma'am.
Okay. So here, the system plus the surrounding, both of them all together is known as a universe. Okay. And the total energy within the universe is assumed to have a constant value. Understood?
Yes, ma'am.
Any doubts?
No, ma'am.
Sure.
So, like, if ask the question, like, state what is a system, then, what, like, which definition should I write, ma'am? Like, what kind of definition should I write?
Okay. If it has been asked that what is a system, then the word itself is defined as the system is the body that we are considering for the heat
Okay, ma'am.
exchange. Yeah.
Okay.
Okay. And the
Yes, ma'am.
place with which we are considering the system is known as the surrounding.
Okay. Yes, ma'am.
Okay. With which we are doing the study of transfer of energy. Understood?
Yes, ma'am.
Now, any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay. So, after this, we are having another thing, and that is okay. Yeah. So, now after this, we are having a closed system and the open system. So sometimes the system is said to be closed. This means that the entities or the particles which are inside the system cannot vary in the number and they cannot go out. So they have a fixed mass with respect to the surrounding. Understood?
Yes, ma'am.
Okay. However, in a closed system, Akshita, the energy can flow into and out of the closed system. Understood?
Yes, ma'am.
Okay, so the mass cannot be exchanged, but the energy can be exchanged. That is known as the closed system. Now, when neither the mass nor the matter nor the energy can enter or leave the system, that system is known as isolated. Okay, so we have basically two types of system. One is known as closed system and another one is known as your isolated system. Okay. So now what is a
Yes, ma'am.
closed system? Only in which energy can be exchanged. Whereas here energy and plus your mass or matter can be exchanged. Understood?
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. So now after this, we are having the next topic and that is the laws of the thermodynamics. So let's do the study of that also. What do we understand by the law of thermodynamics? Okay, so let's do the study of the very first law of thermodynamics. So what does the first law of thermodynamics tell us? It's a basically a very easy thing. Okay, and it said that the total energy of the system, okay, is nothing but the internal energy of the system and plus the work done over the system. Are you getting?
Yes, ma'am.
Okay. Or I should say the heat energy which has been transferred between the system and the surrounding is nothing but the addition of the internal energy of the system and the work done over the system. Understood? And in this chapter, Akshita, you will take care in mind that we will only calculate the work done on the system and we will not calculate the work done by the system. Understood?
Yes, ma'am.
Okay. So here the very first law states us that Q equals to delta U plus W. Now what is here Q? Q is basically meaning that heat transfer. Okay. Now here one thing that arises is if we have plus Q, it tells us that the heat transfer is happening from the surrounding to the system. I told you, no, that plus and on the system and by the system. So it is heat is transferred to the system. Getting?
Yes, ma'am.
And if it is heat is going from the system to the surrounding, then you will write it as minus Q. Any doubts?
Yes, ma'am. No,
Sure?
ma'am. Yes.
Okay, done. So now after this we have delta U. So if my delta U is also plus, that's mean that the internal energy of the system is increasing. If I'm writing delta minus U, it means the same thing, but it is decreasing.
Yes.
Okay, now after this we have plus W, which means that system does work on the surrounding. Okay, whereas minus W indicate us that it is work done from the system or by the system on the surrounding. I mean, surrounding is doing the work on the system. Okay.
Yes, ma'am.
Yeah. So when surrounding is doing some work on system, then it will be minus W. Please note down all these factors. It's very important.
Okay.
Are you done?
No, ma'am. One second.
Yeah, be quick. If the work is happening on the system, it will be minus. If system is doing the work, it will be plus. Okay. If internal energy is decreasing, it will be minus. If internal energy is increasing, it will be plus. Understood?
Yes, ma'am.
Okay. And if the heat transfer is happening on the system, that is heat is given to the system, then it will be a plus. But if the system is giving the heat, it will be minus. Okay. So these are the sign
Yes.
conventions that you have to remember. Any doubts?
No, ma'am. Just can you
Sure.
up a bit, ma'am? Just or can you zoom out, ma'am? That will be zoom. Yes, ma'am.
Like this, in one page you need all this.
Yes, ma'am.
This. Check this.
We have some surroundings. Surroundings. Please.
Are you done?
Just give me a second. Can I just delta W? Yes.
So the total heat energy which has been transferred between the system and the surrounding is the addition of its internal energy and the work done on the system. Okay?
Yes, ma'am. Done, ma'am.
Okay. Fine. So after this, we are having that is pressure volume diagrams. Okay, let's check the pressure volume diagrams now. Okay. This has been explained. Now we are having using the pressure volume diagrams. Just check what happens in the pressure volume diagrams. Okay, I'm giving you the picture.
Yes, ma'am.
Is it visible?
Yes, ma'am.
Okay. What is visible to you?
The whiteboard, but not the image.
Okay.
Like I can see the whiteboard,
Hmm.
but I can't see the image you.
Uploaded, no?
Yes. Maybe
Yeah.
I have to read.
Yeah, exactly. Just give me a sec. I'm doing. Okay. So here is your picture.
Yes, so now I can see two pictures.
I'm deleting the other one. Is it visible?
Yes, ma'am.
Great. So basically what happens over here is, Akshita, that, yeah. Fine. So here we are observing a piston, then the volume which has been increased by applying the piston. Okay, piston is
Yes, ma'am.
going up, piston is going down. You can see here, and this is the delta x which has been the change in volume which has been observed. Okay, when it is going down and when it is going up. Any doubts that you are facing in the diagram?
No, ma'am.
Okay, so here the work done by the gas on the surrounding during the expansion, okay, is
Yes,
equal
ma'am.
to the force of the piston, isn't it?
Yes, ma'am.
What I'm telling is the work done by the gas. Here the gas is filled.
Yes, ma'am.
Okay, so the work done by the gas on the surrounding during the expansion will be equal to the force of the piston, which is nothing but pressure into A, correct? So if suppose I'm applying the force for a distance of delta x, it will be pressure into A, correct? From the
Yes.
formula pressure equals to force over area, I am doing this.
Okay, ma'am.
Any doubts?
No, ma'am.
Okay, so the pressure into area multiplied over a given area, that is delta x, if I am doing, I can even rewrite it as P into A into delta x. Any doubts? Now
Uh,
area into length is nothing but volume, isn't it?
area into what, ma'am?
Area into x, delta x, the length,
Okay. Yes, ma'am. Yes, ma'am.
isn't it? So it will
Yes.
become volume.
Yes, ma'am.
Okay. So here we got that uh, in terms of, if I say the first law of thermodynamics, which tell us that Q equals to U plus W, where Q is the heat exchange, this is the internal energy, this is the work done. I can say that my work done is plus P delta V, because plus work done means what? Plus work done means system is doing work
Assistant.
on the surrounding. So here system is doing the work on the surrounding, that when we push the piston down, what happens? The particular uh, surrounding air, okay,
Yes, ma'am.
basically I should say that the gas is doing work on the surrounding, that when it is expanding, it is making a force on the system, sorry, on the piston only, right?
Can you repeat, ma'am?
Yeah, sure. I'm saying that the work done by the gas, who is doing the work? Gas is doing. Gas is
Gas.
filled where? Inside the
In the
system.
cylinder. Yes, ma'am.
Yeah. So inside the system, gas is doing the work, that when we are pressurizing it, when the piston is moving from up to down, what is happening? It is creating a pressure, isn't
Yes, ma'am.
it?
Yes, ma'am.
So that means all these things is done by the system, hence it will be plus W. Any doubts?
No, ma'am.
Sure.
Yes, ma'am. Sure, ma'am.
Okay. So we can show it as the two pictures are there which can explain this factor. Let me show you those pictures. Check. So if this picture is visible to you here, the graph is given where the area gives the work done by the gas on the surrounding P delta V, isn't it? P into delta V, is it giving? This one?
Yes, ma'am.
Okay. Now in the second picture, what is happening is basically your volume is got increased via this picture, right? That is pressure into delta V got increased over the volume. This is the original volume. This is the blue box have got deposited over here. Understood or not?
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. So from this we can verify the variation of the P with the volume, okay, as a graphical method which tell us that this thing. What does it say? It basically tell us that the work done by the areas of the strip, you have, if you want to calculate the work done, what do you have to do in pressure volume graph? You have to calculate the thorough area under the graph, and as it is integral form, you can see it's a curved path. Hence, what you will do, you will collect the strips and you will calculate the area of each strip. Any doubt?
No, ma'am.
Sure.
Yes, ma'am.
Okay. Shall I give you one question then?
Yes, ma'am.
Okay, let's do one question.
Okay.
Check. Is it visible?
Yes, ma'am.
Okay. So as per this, what do we understand? Monoatomic ideal gas is there, which has been compressed along the path AB. Okay. And you have to calculate the work done during the compression. So how we will calculate the work done? Akshita?
Work done is equal to so 1 second, I'm just taking my booklet. Yes,
I had given you the formula. Work done is calculated
yes,
with
ma'am.
the formula pressure into
The first
change in.
formula I didn't. Oh, the last formula.
Yeah,
The P
obviously.
equal to delta V. That one.
So pressure is how much at AB? 1.5, isn't it? At AB,
One.
how much is the pressure?
A 1 second, ma'am. Calculate 480 K. A B is ma'am. Can I know like how it is like 1.5?
Here it is written pressure, here it is written 10 raised to 5 and 1.5 line is indicating AB.
A B. Okay, ma'am.
And
Okay,
the
the
work is done along the path AB.
yes, ma'am.
Now any doubts?
No, ma'am. So
Sure.
for only the volume, we will take like A minus B like that.
No,
Like
I'm taking
B
the
minus
volume now.
B.
Check. This is my volume. 3 minus 4 into
Yes,
10
ma'am.
raised to minus 3.
Yes,
Or
ma'am.
is it plus 3 or is it minus 3?
I
It is
ma'am,
minus 3. Yeah, it
what
is
I
minus
do
3.
is I would probably do like 4 minus 3 because it is A B. But yeah, B minus C is
Gas is compressed.
yes,
Akshita,
ma'am. Yes,
gas
ma'am.
is compressed.
Yes, ma'am.
So it will be 3 minus 4, no?
Yes, ma'am.
Isn't it?
Yes,
Am
ma'am.
I making sense here?
Yes, ma'am.
Okay. So if it has been compressed, it is coming from A going to B. So this is final position, this is initial position. So B
Yes.
minus A.
Okay, ma'am.
Any doubts now?
No, ma'am.
Okay, go ahead. So I think it will give you the answer 150 joules. Okay.
Yes, ma'am.
Now you understood or not?
Yes, ma'am.
Okay. So now this is done. After this, what do we have? We have that the value of the negative work done shows us that the work done on the system by the surrounding. Isn't it?
Yes, ma'am.
Okay. Now after this, let's take the next question, B pointer. Calculate the temperature of the gas. How can we calculate the temperature? So as the pressure is constant, obviously pressure is constant. Check.
Yes, ma'am.
Pressure is constant.
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. So at constant pressure, which law do we apply? Be quick. In the last class, we had done this.
Constant pressure, it is second law.
Yeah.
P is
Who had given this law?
P1 T. The loser.
Gay-Lussac's law.
L.
Yeah, Gay-Lussac's law is the. Yeah. Okay. So here we can write that temperature with respect to this is becoming with respect to this. Understood? Right or not?
Yes, ma'am. Yes, ma'am.
So temperature at B position will be volume at B position. Volume at B position is how much? 3. Okay, so here I will write 3 into 10 raised to minus 3. Here I will write temperature at A position. The temperature of the gas at A is 480 Kelvin. So here it is 480. Here it is 4 into 10 raised to minus 3. Calculate and give me the answer. Be quick. Are you facing any doubt over here? Akshita?
360.
Are you facing?
Hello, ma'am.
Yeah, I'm asking.
Hello, ma'am.
Yeah, you are audible. Don't. What is the answer?
316.
316. 16.
No, ma'am. 360.
Okay, done. Now understood. So it will be 360 Kelvin. Okay, let's read the next question now. So the next question tell us that determine the change in the internal energy of the gas. Yes.
Determine change in the internal energy of the gas. I change. One second, ma'am. I'm just checking my formula booklet. Ma'am, 1 second.
Uh-oh. Yes, kindly be quick.
Change the 3 by 2 nr delta T.
Okay. So basically we will have the formula delta U equals to 3 by 2 nr delta T. Okay,
Yes.
let's apply the values. 3 by 2 multiply nr delta T. How we can write? Can we write that nr delta T is equal to P delta V?
Yes,
So
ma'am.
can I write P delta V over here?
Yes, ma'am.
Any doubts?
No, ma'am.
This is T. Okay. So ultimately here what will I going to get? I will get 3 by 2 into minus 150. Correct?
Yes, ma'am.
P delta V. We have to calculate now. Check.
Yes, ma'am.
Correct?
Yes, ma'am.
Okay. So here, why did I written minus 150? Tell me.
Because the since the answer was minus like 150 because the pressure goes from A to B. So
minus 225 joule is the answer. Next question. Next it is asking the energy transferred between the gas and the surrounding. Okay. So energy transferred between the gas and the surrounding. Q equals to delta U plus W. So
yes,
minus 225 minus 150. So I think minus 375 joule of energy has been transferred. Correct?
yes, ma'am. Yes, ma'am.
Any doubts?
No, ma'am.
Okay. Now let's come to the next pointer, and that is an ideal gas and the first law.
Like a comparison, ma'am.
Yeah. So basically we have PV diagrams which help us to visualize that there are some changes which take place at constant pressure, which is known as isobaric. Okay. So we have studied this in the last chapter, the laws, right?
Yes.
So I'm
Yes, ma'am.
writing now in writing part. which has been carried out a constant pressure. Any doubts? That is
No,
isobaric.
ma'am.
Okay. Yeah. Now next is isovolumetric. So what is isovolumetric? Basically a change carried out at constant volume. Okay. Then the third one is isothermal. So a change carried out at constant gas temperature, which is constant internal energy. Okay.
Yes, ma'am.
Okay. Now after this we have adiabatic. So what is adiabatic? A change which is carried out with no energy transferred to or from the system. Okay.
Yes, ma'am.
Okay. So in isobaric, Akshita, we carry out all the changes at constant pressure. In isovolumetric, we keep constant volume and keep the things go out and in. Like isovolumetric can be your pressure cooker. Volume is always fixed inside that. Okay. Pressure increases and decreases when the temperature raises and decreases. Correct?
Yes, ma'am.
Isothermal, the change is carried out at the constant temperature. Okay.
Yes, ma'am.
Adiabatic, when there is no transfer of energy between the system and the surrounding. Okay. For example, you can keep the two columns of the, I should say, fridge. They are having no concern and no heat exchange they are doing, but they both are placed in side one system, isn't it?
Yes, ma'am.
Any doubts?
No, ma'am. I'll just take a screenshot of this
Take it.
statement.
Is it
No,
completely
ma'am.
visible?
No, ma'am.
How much it is visible?
Just the last part.
Okay. Just give me a sec. Let me zoom it out. Now is it okay?
Yes. Yes, ma'am.
Okay. So adiabatic basically can be the compression and expansion of the gas by the pistons, right? There the piston is basically giving the diesel engine where no heat is exchanged with the surrounding and the temperature of the gas also remains the same, correct?
Yes, ma'am.
Okay, and the gas expands adiabatically. Okay, like also I can say that when you are shooting a balloon with compressed air, you are releasing compressed air from the balloon to the um, balloon, right? And the air expands
Yes.
rapidly and cools, and it results in the adiabatic expansion only. Okay,
Yes, ma'am.
let me give you another example. It's okay. Akshita, am I audible?
Yes, ma'am. Is there an image like an example, visual example for these?
I will send the image also. But here, suppose I have an insulated system. Okay. And the gas is in the perfectly insulated container I am taking. Okay. And it undergoes a change in pressure. Are you getting?
Yes, ma'am.
Okay. Something like we are having the valve and that is opening up and closing up. So heat is not exchanging,
Mm,
but the system is thermally isolated from the surrounding because
yes,
pressure
ma'am.
is going in and pressure is coming out, right? Now you understood or not?
Yes, yes, ma'am.
Okay. Let me take all of them one by one. Okay. So let's take the very first part and that is isobaric. So in isobaric, what happens is constant pressure is there. Okay. And in this, the first law of thermodynamic is basically written as Q equals to delta U T V. Correct or not?
Yes, ma'am.
I'm saying at in isobaric change, what happens is it is occurring at the constant pressure, right? So the pressure
Yes, ma'am.
is constant. What is changing? The energy and the work done. Volume.
Yes, ma'am.
Right?
Yes, yes,
At
ma'am.
constant pressure, the internal energy and the volume is changing for the heat exchange of the system. Are you facing any doubts now?
No, ma'am.
Okay. So the equation can be written here as V over T is basically a constant value for the system. Okay. Now let's talk about isovolumetric. I'm explaining you this part also. Don't worry with the example. Okay. So what is isovolumetric? In isovolumetric, the volume of the gas remains the constant. That means the pressure over temperature will be a constant value. Okay. Because when volume is constant, pressure is directly proportional to temperature. Okay,
Yes, ma'am.
done. So when the volume is,
Yes,
I had given you the example. Example is pressure cooker.
yes, ma'am.
There the volume is constant. And
Yes, ma'am.
inside that, when we are increasing the temperature, the pressure becomes so high that it shoots out with the whistle.
Yes, ma'am.
Any doubts?
No, ma'am.
Done. So here my first law of thermodynamics, that is delta U plus P delta V. So in this, the volume is not changing. This is 0. Hence, it will be Q equals to delta U only. That means internal energy is making the change and the heat change in the system. Understood or not?
Yes, ma'am.
Okay. Here the all the heat energy transferred into the system and it appears to be the internal energy of the system. You will see the vibrations of the particles in the system and due to that you will see the pressure has been created inside the system. Again, I am giving you the example of pressure cooker only. You will see the vibration from your own eyes. Right?
Yes.
Now any doubts? Akshita, your voice is going
Hello,
and
ma'am.
coming. You are not
Hello, ma'am.
audible.
Hello,
Yeah,
ma'am.
hello. Yeah, hello.
My
Hello.
voice
You are on.
breaking.
Yeah, your voice is breaking. My
Yeah,
voice
yeah,
is
yeah.
to.
My voice. Yeah, is my voice breaking, ma'am? Should I rejoin?
Nah, no, no, no. Please don't rejoin. Only 10 minutes are left. We should not waste the
Okay.
time. Yeah.
Yes.
Okay. Isothermal change. Now observe the isothermal change. Okay. So basically, there are isothermal means temperature remains the constant.
Yes, ma'am.
Thermal means what? Temperature remains the constant, right?
Yes, ma'am.
What we had written. Check. A change carried out at constant gas temperature where the which is constant internal energy of the system. Okay,
Yes, ma'am.
so here internal energy remains constant first thing, and then the temperature also remains unchanged. So my this law, internal energy is constant, right?
Yes, ma'am.
So this will become 0. Hence my total heat is given due to the work done on the system. Any doubts?
No, ma'am.
Okay. So if I am having plus W, so it simply means that the gas in the container is expanding. And if it is minus W, it simply means the gas is compressing inside the system. If it is compressing, means surrounding is doing the work over the system. And if it is expanding, that means system is doing this work over the surrounding, right?
Yes, ma'am.
Any doubt?
No, ma'am.
Okay. And here the system is contracting. Okay. Let me show you the graphs. Please observe the graphs of all the three things. Okay. So this is the graph for isothermal. Check. Okay.
Yes, ma'am.
Okay. Now this is the graph for isovolumetric. Check. Correct?
Yes, ma'am.
Volume is remaining the constant. Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Last is adiabatic change. Let me explain you adiabatic expansion also. This is adiabatic. Okay. What happens is when no energy is transferred between the system and the surrounding, it is known as adiabatic. Okay.
Yes, ma'am.
And this is achieved when the insulating boundary you have between the system and the surrounding. That means
Yes,
no heat exchange should be there between system and surrounding. If this is my system and this is my surrounding, the wall should be completely insulating. So no exchange of heat should be occurring. Any doubts?
no, ma'am.
So the Newton's first law, that is delta U plus W, will be such that no heat exchange is happening. Hence, Q will become 0. So the total energy change will be equal to the work done. So either it will be minus U or W, or it could be minus W equals to delta U. Correct?
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. So when we are writing minus U plus W, it simply means that the work done on the system with an increase in the internal energy. What is minus delta U? Let's read again. Here, internal energy is decreasing. Here, internal energy of the system is increasing. Plus.
Yes,
Okay,
ma'am.
so this we are talking about inside the system and outside the system. So here the internal energy of the system is increasing and internal energy of the surrounding is increasing. And here the work done is plus. That means work done on the system is plus and by the system is 0. Here work done by the system is highest, minus W. Correct?
Yes, ma'am.
Okay. And that is basically decreasing the internal energy. Now you getting here the
Yes.
internal energy decreasing. Is it? Okay. Any doubts now?
No, ma'am.
Sure.
Yes,
So
ma'am.
from combining all of them, we get a law which is P1 V1 over T1 equals to P2 V2 over T2. Okay.
Yes, ma'am. So will there be questions regarding these, the not this formula, all the work done, the
No,
other
they will be asking you. They will be asking you the formula separately also and in theoretical part also. So I am explaining you all the things. Okay.
Yes, ma'am.
They will ask you what is adiabatic exchange. Okay.
Yes, ma'am.
And give the examples. How will you elaborate the plus W? If there is any system, how will you say what are the sign conventions that you are observing? Is it W plus W? Is it minus W? Is it plus C minus C? Like that, they will ask you. Understood?
Okay, ma'am.
So you will be able to know. Now, any doubts here?
No, ma'am.
Sure. So now the next part is Carnot cycle and Carnot engine. So basically the Carnot engine is shown like this. Have you seen the heat engine of a vehicle?
Heat engine of like no, ma'am, not like an actual one in real life.
Okay, not an issue. Check. Okay. So when the system is going from here to here, here to here, okay, it's going, yeah, it's going ulta. Okay. So when it is going A to B, you can see pressure and volume. The volume is decreasing.
Yes, ma'am.
The pressure is decreasing and the volume is increasing, isn't it?
Volume is increasing. Yes, ma'am.
Isn't it? Yeah.
Yes, ma'am.
So which process it is? Isothermal or isobaric or iso what?
Since pressure is decreasing, and then
It will be isothermal because temperature is
isothermal.
constant. Yeah.
Yes,
Okay. Yeah.
yes.
Now have a look over here. B to C. Here what is happening?
B to C is also the same thing. Oh, okay, ma'am. One second. The arrows is it opposite? Like,
It's okay. It's okay. Akshita, don't worry. Don't worry. I'm explaining. So this particular part is isothermal expansion. Isn't it?
yes, ma'am.
Here. Okay. Now, if I take B to C part, that is what I had asked from you. It will be adiabatic expansion.
Okay, ma'am.
No heat is exchanging. Okay. Now, if I explain this particular part, it will be isothermal compression. It is compressing. See, it is compressing towards up again. Okay, I'll explain you this part. Don't worry. And then this is adiabatic compression.
Hello, ma'am.
Yeah, hello. Am I audible?
Yes, ma'am. My network connection just it went.
Oh, so fine, Akshita. if it is like that, I would say that we will continue this part tomorrow. Only this part is remaining in this chapter. Don't worry. Okay. Other parts I had already finished. Okay. Just the opposite of that, that is refrigerator, and this part is remaining. Okay. And we will complete it in the next class. Then we will start the next lesson also. Okay.
Yes, ma'am.
Okay. Please try to join early in the class. Okay.
Yes, ma'am. Yes, ma'am.
Okay, no issue. Fine. Bye, Akshita. Have a nice day.
Yes, ma'am. I just wanted to ask a question, ma'am.
Yeah, say
Where
Akshita.
do you like generally like questions, like more questions, topic wise questions? Do
You
you have
need?
like a resource?
Yeah,
Yes,
yeah.
ma'am.
I'll give it to Miss Sonia. She will give it to you. Okay. I have,
Okay,
and I will
ma'am.
send it to Miss Sonia, and she will pass it to you. Okay. For thermodynamics, you need right now.
Yes, ma'am.
Okay, I'll send it to Miss Sonia. Don't worry.
Okay, ma'am.
Okay. Bye.
Bye, ma'am. Thank you, ma'am.
Yeah, I'll send you the marking scheme also.